Hello, my name is Ken Embury and I'm the Product Manager for ORTEC Electronics and Software. Thank you for taking time to learn more about our new advanced multi-channel analyzers for gamma spectroscopy. This presentation will cover the new instrument models and features, including digital coincidence timing, web interfaces, expanded ADC conversion gain, and an update to our connections driver software. The new MCA models are the DSpec 50A and DSpec 502A with 1 or 2 MCAs respectively. These spectrometers are physically identical to the standard DSpec 50 and 502 instruments, but offer new advanced features. We also have a DSpec upgrade model to convert the standard DSpec 50 and 502 to their respective advanced models. This is a firmware and software upgrade, but does require the units to be sent back to the factory to verify that the instrument operates as expected after the upgrade. We have some exciting new features in the advanced MCAs. First, let's talk about the digital coincidence timing, which is enabled through configurable output and gate ports with digital counters. This feature was added to simplify Compton suppression and cosmic veto systems while also achieving superior performance. Existing users of Compton suppression and cosmic veto systems can benefit immediately, as the DSpec 502A is a drop-in replacement for the existing electronics. This capability also opens the door to offer standard digital Compton suppression and cosmic veto systems going forward. In order to understand the benefits of a Compton suppression and cosmic veto system, we should first review the photon interactions with matter and the spectrum artifacts that arise from these interactions. The 3 key interaction processes are photoelectric effect, Compton scattering, and pair production. With photoelectric effect, all of the photon energy is transferred to an electron in the orbital shell of an atom. This is the predominant interaction for low energy photons. If the photon has sufficient energy to free the electron from its orbit, then a pulse proportional to the incident photon energy is registered in the electronics, and multiple events of this type give rise to a full energy peak in the low energy portion of the spectrum. Compton scattering occurs when some of the photon energy is transferred to an orbital electron and some of the photon energy scatters off in a different direction. The scattered photons may go on to interact with other electrons or escape the detector. If the scattered photon leaves the detector, then the pulse registered in the electronics is not representative of the original photon energy, but rather some lower variable amount of energy that results in the large Compton continuum shown here. High energy photons, somewhat greater than 1022 keV, can spontaneously convert to an electron and positron when traveling through the Coulomb field of an atom's nucleus. The positron will then go on to combine with an electron, with their annihilation converting mass back to equivalent energy, with 2 511 keV photons emitted in opposite directions. If one or both of these annihilation photons leave the detector, then we end up with the characteristic single and double escape peaks in the spectrum at 511 and 1022 keV below the full energy peak. These photons may also go on to interact by Compton scattering with a potential for some non-discrete energy loss, which adds to the Compton continuum. If all of the incident photon energy is retained in the detector, then the electronics will register a pulse equivalent to the incident photon energy, and a full energy peak will develop in the spectrum as data is acquired. This is the signal of interest for nuclide identification. These photon interactions can also occur in the shield and scatter back towards the detector, giving rise to distinct spectral artifacts such as the annihilation peak at 511 keV from pair production in the shield, a less discrete peak around 200 keV due to Compton scattering in the shield, and X-rays generated by electron energy transitions that follow ionization from the incident photons. Having reviewed the photon interactions, we can better understand what is meant by noise in the spectrum. Noise is any spectral data that isn't a photopeak or signal of interest. We commonly refer to this noise as background, but more precisely we mean the background in the vicinity of the peak of interest. The peak background is dependent on the environmental background as well as radioactivity within the sample itself, and affects our ability to detect peaks of interest. This detectability is usually referred to as a minimum detectable activity or lower limit of detection, which is proportional to the square root of the peak background. So what are the sources of this noise or peak background contribution? One source is the detector itself, which can contain small amounts of radioactivity. This contribution can be minimized by using low background materials in the construction of the detector. Radioactive material in the vicinity of the detector, such as naturally occurring radioactive material, stored samples, and radiation fields from operations in a nuclear plant, can also increase the background. Low background shielding is very effective at reducing this contribution, but cosmic and background veto systems can also help. Muons, which are very high energy electrons generated by cosmic interactions in the atmosphere, can penetrate deep in the shield with their scatter photons reaching the detector. This contribution can be reduced by placing the detection system far below ground, which isn't practical for most cases, or using a cosmic veto system. We can also have photons emitted from the sample that deposit only a portion of their energy in the detector due to escaping Compton scatter or annihilation photons as discussed in the previous slide. The probability of scattered photons leaving the detector can be reduced by using larger detectors, and Compton suppression systems can help reduce the impact of scatter photons that do leave the detector. Finally, we have photons emitted from the sample that interact with the shield and the resulting scatter photons and X-rays emitted in the direction of the detector. This impact can be reduced by keeping the shield as far as practical from the detector, lining the shield with tin and copper to attenuate low energy X-rays, and using a Compton suppression system. So how does a cosmic and background veto system work? Basically, we place plastic scintillator detectors on top of the shield or completely surround it and cancel events that occur in the high purity germanium detector and these veto detectors at the same time. In many systems, most of the external background can be attributed to muons, which predominantly travel in the vertical direction and are easily detected by fairly thin plastic scintillator detectors. Using one of these large area detector panels on top of the shield, a cosmic veto system can reduce background in the high purity germanium detector by around 30%. A low background system tested at Lawrence Berkeley National Lab with plastic panels that completely surrounded the shield for cosmic and localized background veto reduced background in the high purity germanium detector by nearly 90% over a 3.6 MeV energy range. With a Compton suppression system, the veto detector is inside the shield. It consists of an annulus that wraps around the high purity germanium detector and a plug detector on the face of the high purity germanium detector. Some systems also have a back shield around the cryostat. Events that occur in the high purity germanium detector and the veto detector at the same time are eliminated to reduce background predominantly from Compton scattering. Here are a couple of Compton suppression system example spectra with the suppressed or anti-Compton spectrum overlaid on the full or uncorrected spectrum. On the left we have cobalt-60, which has a large Compton continuum with the characteristic Compton edges a few hundred keV below the primary photo peaks, and a large backscatter peak at the lower end of the Compton continuum from backscatter photons from the annulus detector and from the shield to a lesser degree. This overall Compton background region is reduced by 94%, which significantly improves peak detection in this region. But since the 1173 and 1332 keV peaks are emitted in cascade nearly every decay, we also reduce the primary photopeak areas by 75% in this system because the coincidence detection is basically the same as a Compton scattering event to our system. A different size or material veto detector could result in even greater reduction in the primary photopeaks due to better detection efficiency for these fairly high energy photons. Nuclides with cascade photoemissions like cobalt-60 require the full or uncorrected spectrum for accurate activity quantification. The cesium-137 example on the right also shows a significant reduction in the Compton continuum as expected. However, the primary gamma ray emission peak is nearly identical in both the full spectrum and the anti-Compton spectrum, making it a good candidate for quantification in a Compton suppressed spectrum. The key takeaway is that Compton suppression systems are intended to improve detection of certain isotopes, but the full spectrum must be retained for proper quantification of others if they are of interest. Different nuclide libraries are commonly used for analysis of the full and anti-Compton spectra, but different analysis settings and even calibrations may also be desired. This example demonstrates how a small peak buried in the Compton continuum becomes much more obvious when the coincidence Compton events are eliminated. When viewing the full or uncorrected spectrum in log scale, there is no discernible peak, and spectrum analysis algorithms are unlikely to find a peak due to the high uncertainty. But a peak search should easily identify this peak in the anti-Compton spectrum, as the uncertainty is much better. Compton suppression systems capable of achieving peak-to-Compton ratios greater than 1,000 to 1 have actually been around for many years, but they were very complicated to set up and maintain with numerous NIM modules. Most of us wouldn't have a clue where to even start with this complex configuration. An initial setup can take up to a few days even by the experts, so imagine how frustrating this type of system must be in the field and why the concept has not been adopted more broadly in the market. The new digital coincidence timing capabilities of the DSpec 502A greatly simplify the system configuration and operation, with initial setup completed in well under an hour. The only other component that may be needed is a power supply to accommodate the high current needs of some scintillation detector configurations. The digital coincidence timing is enabled in the new advanced MCAs through configurable output and gate ports and digital counters. The output port is the existing change sample port with new options in the MCB properties to define what drives pulses to be sent out. The options are the traditional change sample command, which now has an optional pulse width capability, CRM, which is the count rate meter that is initiated by the fast discriminator, SCA or single channel analyzer, which generates a pulse when the full energy peak falls within a specified region of interest, and ADC gate that fires when the gate is active. The configurable gate consists of coincidence and gate logic for very precise evaluation of pulses between the input gate and the fast discriminator in the pulse processing circuit. Gate route mode can also be enabled to store all spectrum events simultaneously as gated or ungated and save these spectra along with a combination of the two for a total spectrum in a single ANSI N42 spectrum file. The sample ready and gate input ports now have counters available that are synchronized with spectrum acquisition. These counters can be used for any TTL input pulses, but are very useful in the coincidence timing setup. We also added the ability to easily disable pileup rejection, primarily for diagnostics, and manually adjust the fast channel threshold for optimization of coincidence timing in the MCB properties. To better understand how this digital coincidence and gate logic works, it's probably a good idea to review the pulse processing circuitry. The signal processing is initiated by the fast amplifier. This circuit is used to rapidly detect a deviation from the signal baseline, which indicates the arrival of a photon in the detector. The fast discriminator threshold is normally set just above the noise level automatically, but can be manually adjusted for certain situations as mentioned in the previous slide. The fast discriminator triggers the start of an inspection interval for the pileup rejection circuit and for the slow amplifier to start measuring the pulse amplitude. Analog systems define the pulse measurement time as shaping time, whereas digital systems use a trapezoidal filter with rise time and flat top settings. This pulse processing time defines when the pulse height is stored to memory in the appropriate spectrum channel and the time allocated for the signal to return to baseline before another pulse can be accurately measured. The pileup rejection circuit ensures that pulses have sufficient time to be processed. If a second pulse arrives while a previous pulse is being processed, then an inhibit circuit effectively stops the lifetime clock for the pulse processing period, creating dead time in the system, and neither pulse is stored to memory. The coincidence timing logic is configured based on our understanding of the fast discriminator defining the photon arrival time and the slow amplifier defining the time the pulse is stored to memory. Let's start with the back panel BNC connections on the DSpec 502A. The lower connections are associated with MCA1, which will have the energy input from the high purity germanium detector. The upper connections are associated with MCA2, which will have the energy input from the Veto detector, either sodium iodide or plastic panels, depending on the system. The output port, which is labeled as change sample from MCA2, will be connected to the gate port on MCA1. The output in MCA2 must be set to CRM to send a TTL pulse to the MCA1 gate whenever the fast discriminator signals a photon arrival in the Veto detector. These events can be tracked using MCA1's digital counter B. The output port from MCA1 will be connected to the sample ready port on MCA1 with the output set to ADC gate so that we can track when the coincidence gate is applied using MCA1's digital counter A. In the MCB properties for MCA1, which is the high purity germanium detector, we set the gate to coincidence, enable the coincidence logic option, and set the delay and window values as necessary to define when photons arriving in the Veto and high purity germanium detectors are close enough to be associated with a common origin. Recall that the fast discriminator indicates the beginning of a pulse to be processed, which correlates to the arrival of the photon. The gate signal is generated from the Veto detector based on the arrival of a photon there as well. Several factors can affect the time at which coincidence pulses are generated and detected on each end of the logic tree, but the difference is pretty consistent with a particular configuration. If the gate pulse from the Veto detector occurs before the fast discriminator on the high purity germanium detector, then we simply add a delay to align coincidence events to a common start time for comparison. If the gate signal comes in after the fast discriminator, then we use a negative delay to align the event times. The delay can be adjusted in 25 nanosecond increments to just over 6 microseconds. With the photon arrival time synchronized to a common starting point, we set a time window to define which events are considered in coincidence. Either the gate or fast discriminator can trigger the start, and a corresponding event from the other signal within the coincidence window will satisfy the coincidence logic. The window can be set a little over 6 microseconds, but it should be noted that good coincidence correlation is usually no more than a few hundred nanoseconds. When the coincidence logic is satisfied, the gate must be applied at the time the event is stored to memory. Recall that this time is based on the rise time and flat top associated with the slow amplifier. The gate delay specifies how long to wait after coincidence is determined before the gate is enabled, and the window defines how long the gate will be held active. Note that the gate position can shift up to the maximum width of the coincidence window, so we generally use a broad gate band to ensure that it covers the pulse height detection time. If the gate logic is applied when the pulse is stored, then a TTL pulse is generated on the output of the high purity germanium detector, since we set it to the ADC gate option. Now we can compare the frequency of events from the Veto detector that were in coincidence with those in the high purity germanium detector and optimize the various parameters accordingly. Gate route mode can also be enabled to store the gated and ungated events simultaneously and save them along with the total spectrum in the N42 spectrum format for subsequent analysis with the appropriate calibrations, nuclide libraries, and other analysis settings. An Excel program to help automate the digital coincidence timing setup is available for download from the ORTEC website on the DSpec 50 webpage. This program is designed to optimize the coincidence delay and window in a Compton suppression system using cesium-137. After connecting the cables and setting the output options as described in the previous slide, 3 regions of interest are set in the high purity germanium detector to cover the cesium-137 full energy peak, the Compton continuum below this peak, and the higher energy region above it. While using a narrow coincidence window, the Excel program will change the delay in negative increments of 25 nanoseconds in successive measurements while monitoring the coincidence count rate on the sample ready port. The coincidence count rate will normally increase as the gate and fast discriminators become better aligned and then drop off as additional delay causes them to diverge. Then the delay is adjusted in the opposite direction until the coincidence count rate is maximized on the sample ready port. The coincidence delay is then set to the optimized setting while the coincidence window is opened in 25 nanosecond increments. The optimal window setting may be dependent on the count rate of samples being measured, but in general, the optimal window is found when wider settings show no significant increase in the coincidence count rate. While data is being collected, you should notice that the coincidence count rate on the sample ready port and the Compton Continuum region of interest are very similar. As the width of the window increases, these parameters will start to deviate as the coincidence logic is being triggered by random events rather than scatter photons associated with a common origin. This random coincidence when the window is too wide can also be identified by an increase in the cesium-137 full energy peak count rate because there aren't any coincident scatter photons to correlate when all of the original photon energy is collected in the detector. Let's take a look at how this process works in an accelerated timescale. First, we optimize the coincidence delay and acquire data. The optimal coincidence delay is based on the ADC count rate as indicated on the sample ready port counter. Now we can start opening the coincidence window while monitoring the coincidence count rate on the sample ready port. The coincidence count rate initially increases rapidly and eventually levels off, with the optimal setting being at the inflection point between the two. As mentioned previously, gate route mode is the ideal acquisition method for coincidence systems because the gated, ungated, and total spectrum is stored simultaneously. An example gamma vision job to extract each spectrum in an N42 spectrum file for further analysis is also available for download from the ORTEC website. Aside from greatly simplifying the configuration process, the digital coincidence timing performance is outstanding. Here we see examples of data collected from a standard Compton suppression system. The NIM configuration shown at the bottom generated very good results with a peak to Compton of 1119:1, but the digital system far exceeded expectations with peak to Compton of 1355. Now let's move on to the new web interfaces. The web interfaces consist of a web page and web service programming interface, which are operating system independent. These features will enable customers using Linux, Macintosh or Apple, and even Android devices to use our instrumentation. System integrators, researchers, and web application developers will also benefit from the new web interface tools. The web page interface provides basic MCA emulation, including spectrum acquisition and setting hardware properties. The web page is hosted on the instrument and can be accessed using any modern browser run from any operating system. This includes not only computers, but tablets, iPads, and even your phone when these devices are connected to a common network. And accessing the web page and communicating with the instrument requires absolutely no software installation whatsoever. The web page consists of a main screen where the spectrum can be acquired and stored, as well as tabs at the top of the page to access the hardware properties. These property pages have the same parameters as the corresponding MCB property tabs accessed through standard ORTEC software such as Gamma Vision. The Web Services Programming Interface is operating system and programming environment independent as long as Web Services is supported by the development tools. No software installation is necessary, and similar to the web page, the Web Services Interface is hosted directly on the instrument. The Web Service Interface is similar to the A11 Toolkit as developers can write their own applications to establish communication with the instrument, issue commands, collect spectra, and even save a spectrum file to the new N42 format. A programming example to help customers get started is available from the ORTEC website on the DSpec 50 page, and we're anticipating more examples to be available in the future. The next new feature in the advanced MCA models is the expansion of the ADC conversion gain from the previous maximum of 16,000 channels to over 64,000. Having so many channels in the spectrum offers superior peak fitting in the lower energy regions of the spectrum, when very high energy peaks are also of interest in the measurement. Here is an example of a 12 MeV energy range of interest using 64K and 16K spectra. The data available with the higher energy peaks, just under 3 MeV in this case, is very similar as shown in the gross and net peak count rates. It's also interesting to see how much spectral data is available in the higher energy region from cosmic background. But when we look at the low energy peaks in these spectra, we see that the 64K spectrum has much better separation. The inadequate separation of peaks in the 16K spectrum distorts the baseline enough to significantly underestimate the net peak count rate. When running a peak search in the low energy region of these spectra, it is easy to understand why some of the more obvious peaks that are fit well as multiplets in the 64K spectrum are completely missed in the 16K spectrum. Finally, we have updated connections to version 9. This update supports the new DSpec 50A and 502A firmware, but it also resolves a critical issue that recently arose with the Windows 10 driver signing compatibility and a lesser-known issue where a DSpec 502 could freeze when one MCA is in list mode while the other is in PHA mode. Version 9 will ship as standard going forward and can be made available by AMFX at no charge to any customers experiencing the incompatible driver signing or instrument freeze issues. In summary, we have discussed the new features in the advanced DSpec 50A and 502A, including digital coincidence timing to simplify Compton suppression and cosmic veto systems with superior performance, web page and web services programming interfaces so the instrument can be used without a Windows-based computer, the ADC conversion gain expansion to 64K for superior low energy peak separation and fit when very high energy peaks are also of interest, and Connections version 9 to support the new instrument firmware, Windows 10 driver signing compatibility, and to resolve a legacy issue with the DSpec 502. I hope you have enjoyed this presentation. Feel free to call or email me with any questions or comments that may arise in the future. Thank you.